So in this section, we're going to talk about what streams are and also how they relate to other concepts that you might have heard. You might have heard of reactive streams. And of course, we're talking about Akka. So how does it relate to Akka? So we're going to cover all of those things. And we're also going to introduce you a little bit to the basics of streams. So what are streams? Streams are sequences of data that are divided up into individual elements. The size of the stream may not be known, or it may in fact be infinite. Often these streams are too large to fit in memory. Basically what this means is that you have this stream of data, whatever that data may be, and you don't know without consuming the data how much data is going to be there. So it may be infinite. Or it may not be infinite, but if it's too large to fit in memory, you can think of that as kind of functionally infinite, because from the memory's perspective, it might as well be infinite. It can't fit. So some examples of this are the Twitter fire hose of tweets, live video streams, data from fitness tracker. So the Twitter fire hose of tweets are going constantly. There is a lot of tweets out there, and we definitely cannot fit those in memory. But more importantly, as long as you are continuing to consume them, you will get more tweets. Until, of course, maybe Twitter shuts down at some far distant point in the future. But functionally, we can think of that as being an infinite stream of data. Live video streams. So if you have a camera pointed at a location and you are just recording data, until that camera is turned off, we're going to continue to record data. So the problem here is we don't know when that camera could get turned off. It could get turned off anytime or not at all. If it's turned off not at all, then we don't know. It's an infinite stream of data. But until it gets turned off, we can't figure out how much data we're going to be consuming. So again, this is basically a functionally infinite stream of data. Data from a fitness tracker, the same thing. As long as you're wearing that fitness tracker and the battery hasn't died, that can continue to produce data. So again, this is somewhere that we could leverage a stream. So what are some use cases for streams? Consuming live events such as tweets we talked about, or the fitness tracker is another good example of that. ETL systems are a good example, extract, transform, load. If you don't know what that means, basically that is consuming data from one location, transforming it, and then loading it into another location. That the original and endpoints could be databases, files, etc. But the problem with ETL systems is that often they are very, very large files or databases that are being consumed. And so you can't necessarily fit them all in memory, and you don't necessarily want to read the entire file in order to figure out how big it was prior to consuming it. I mean, oftentimes you'll have you might be able to find the name or the size of the file, but sometimes it's not a file. Sometimes it's a database, sometimes it's a REST API or something else. So we don't always know ahead of time how big those are going to be, and they can end up being many, many gigabytes. Streaming media is another good example. We talked about the live video example, but it doesn't have to be live video. It could be any kind of video. But often if you're dealing with high definition video, you're getting into many, many gigabytes of data. And again, that's not necessarily going to fit into memory. So that's streams, but you may have heard this term reactive streams. So what is reactive streams and how does it relate? Reactive streams is an initiative to provide a standard for asynchronous stream processing with non-blocking back pressure. This encompasses efforts aimed at runtime environments such as the JVM and JavaScript, as well as network protocols. There's a link down there at the bottom which will take you to the Reactive Streams website. If you feel like learning more, we'll go into a little bit of detail. We're not going to go into all of the detail, but this is basically just a quote off of that website. So why do we need reactive streams? So when we're consuming our streams of data, we can consume them synchronously or we can consume them asynchronously. If we consume them synchronously, the problem is that we are not leveraging the full resources of the machine. We are using a single thread and a single processor. That's not very efficient when we're trying to consume large amounts of data. So we need a way to consume them asynchronously so that we can do things in parallel and therefore leverage more of the machine. The other question is, how can we prevent an asynchronous stream from overwhelming a slow consumer? So if you've ever built an asynchronous stream of data using actors, for example, or even using futures, then you may have encountered situations where you have a slow consumer, and as a result of that, maybe you're spawning too many futures and running out of memory, or maybe if you're using actors, you've overflowed a mailbox because the consumer just couldn't keep up with the data that you're giving it. So we need a way to prevent that. Then the other thing is, when you're dealing with asynchronous processes, oftentimes you lose your ordering guarantees. But we don't want to necessarily lose our ordering guarantees. So we want to maintain ordering, but still process asynchronously. So if we were to just take our data and chunk it up into pieces and then send each of those pieces off into futures and then bring those futures back together, we would have to have a way to merge that in order to figure out the ordering. Actors, if we use actors, give us some ordering guarantees depending on how we use the actors. But if we're just using a single actor and dumping data into it, then yes, we get the ordering guarantee, but we don't really get the asynchrony. So we're trying to figure out a way to blend these things. So what are the components of reactive streams? Reactive streams consist of a publisher. The job of a publisher is to publish data into the stream. We have subscribers who consume data from the stream. And then we have processors. These act as both a publisher and a subscriber, and they obey the contract for each. Then we have a subscription which connects a subscriber to a publisher in order to initiate the message flow. So publisher, subscriber, and processor by themselves don't really do anything. They're basically templates explaining how to do things once we connect everything together. The subscription is then what connects everything together. These are kind of low-level concepts in reactive streams. We don't necessarily deal with these directly when dealing with Akka streams. The idea behind these components is that they're intended to be sort of low-level, and then you build APIs on top of them. Another important note is that a publisher is forbidden from sending data downstream until the demand has been signaled. And we'll look at that a little bit more when we talk about back pressure. So what is back pressure and how is it implemented? So it is implemented using a pull-push type mechanism. You can see in the diagram here. So the publisher is going to send data downstream. We have a publisher, a processor, and subscriber. The processor is going to receive that data and then send it on to the subscriber. In the meantime, the subscriber is sending requests upstream to the processor and eventually to the publisher, signaling demand. So what happens is a subscriber will signal demand. That gets sent all the way upstream through the subscription. Then the publisher is going to receive the demand, and if it has any data, it will push it back downstream. And again, publishers are forbidden from pushing more than the demand, and that's what creates our back pressure. If the subscriber has not signaled that it is ready for more data, then the publisher is not allowed to push it. So what is Akka Streams' relationship to reactive streams? Akka Streams is built on the concepts and interfaces of reactive streams, but provides an API that is geared towards end users. So again, the reactive streams API was not really intended to be an end user API. It was sort of like, you could use the example of TCP, for example. When we do network communication, we often don't deal with the nitty-gritty details of TCP directly. That's abstracted by the libraries. So reactive streams is the same kind of idea. It provides the protocol, and then we build libraries on top of that protocol. We don't necessarily want to interact with the protocol at all times. Akka Streams does expose some points of interoperability between reactive streams and Akka Streams. So if you have other libraries that are built using reactive streams and you want to connect them up with Akka Streams, you can use these interoperability points to do that. If you're interested in more implementations of reactive streams, Wikipedia has a few examples, but there's probably more that aren't included on Wikipedia as well. So how are Akka Streams then related to Akka actors? So actors consume streams of data in the form of messages. Those messages are basically a stream of data. That's what they are. The problem is it can be tedious and error prone to implement streams with back pressure between actors manually. So if you were to go ahead and try to implement Akka Stream type functionality using just actors, you could do it, but it's going to be a little tedious and you might make mistakes. So Akka Streams just kind of takes that away from you and does the work for you. It also provides a higher level API for stream processing that is backed by Akka actors. So if you actually look at how Akka Streams are implemented, they are implemented under the hood using actors, but they're a higher level API on top of those actors. The other thing is Akka Streams provide static type guarantees that prevent wiring errors. So if you've done a lot of work with Akka, then you'll know that by default Akka is not strongly typed. And that can create problems, obviously. If we can get the compiler to do the work for us, that's always a good thing. So Akka Streams just provides a higher level API that gives you that stronger typing. Of course, Akka does have Akka Typed, which is an experimental module right now that does provide stronger typing. But again, that is an experimental module. So what is an Akka Stream? Now that we understand the relationship to all of these concepts, what is it really? So in an Akka Stream, data flows through a chain of processing stages. Stages then consist of 0 or more inputs and 0 or more outputs. However, they must have at least one input or output. They can have more than one input or more than one output, but they have to have at least one of either. By default, these stages are fused together to run synchronously inside of a single actor. We'll talk more about fusion later, but they can be made to run asynchronously in separate actors. So they're fused because it provides an efficiency bonus, but by fusing them in that way, you lose out on a lot of the asynchrony. And so you can then break up the individual stages asynchronously in order to gain the asynchronous bonus. So this is an example of a linear stream. We have a file. We have a source that is consuming from that file. We have a flow that is performing some map operation on the data from the file. And then we have a sink, which is then writing to a database. So a source in an Akka stream is the source of the data. This is where the data is coming from. The sink is the destination for the data in the stream. And then we have flows, which are transformations to the data in the stream. When we take a source and connect it to a sink, possibly through one or more flows, we create what's called a runnable graph. And this is a stream where all inputs and outputs are connected. And this is the point where we can run the graph and start consuming data. Each stage in the stream can be executed synchronously or asynchronously. So the default is to roll all of the stages into a synchronous stream. But we can introduce asynchronous boundaries at any point in order to run pieces of it asynchronously. In most cases, element order is preserved, but there are certain operations that we can do that will not preserve element order, and we'll give some examples of that as we go. Back pressure is propagated from downstream stages to upstream. So similar to reactive streams, in Akka streams, a sink will communicate demand upstream. It'll go through the flows and up into the sources in order to communicate demand and create back pressure. Linear streams are often sufficient for most use cases. Generally speaking, you may not need to go beyond linear streams in order to get the work done that you need to. However, not always. There is a small set of use cases where you need to get into something more complicated. In that case, we can start leveraging graphs. Graphs introduce something called junctions, which are branch points in the stream. Examples of this would be fan in or fan out. And they allow us to build complex flows of data with multiple inputs and outputs. So in this case, we actually have three sources. We have a fan in that's taking two of those sources and essentially merging it into a single source. And then we have another source that goes into a fan out, which takes that single source and basically creates two sources out of it. We then move that data into a fan in or into a flow, and then eventually it goes back into a couple of sinks. So here's an example of a very simple linear stream. We have a source 1 to 10, so this is the numbers from 1 to 10, and then we are going to push those numbers into a flow. That flow is going to map the data, basically multiplying each number by 2, and then we're going to take that and we're going to push it into a sink, and the sink is just going to do a simple print line, and then we're going to run it. So the result of this will produce the numbers 2, 4, 6, 8, 10, etc., all the way up to 20, and it will produce it 1 per line because we're doing a print line. Now, a thing to keep in mind is that sources, flows, sinks, and junctions are immutable, reusable templates. They basically contain instructions on how to produce, transform, or consume data, but by themselves, they actually don't do anything. In order to start the flow of data, you have to materialize the graph, and we'll talk more about materialization. You can think of this maybe from the perspective of an assembly line. So if you have a bunch of people working on an assembly line, those people know how to do the work. They know how to do whatever is required at their station. They have the necessary instructions. But until they are actually standing on the assembly line doing the work, those instructions don't do anything. You know, if they're sitting eating their lunch, those instructions are present, but they don't do anything. The person has to be assigned to the assembly line before the work will start. And that's essentially what materialization is. It's taking these instructions and assigning them to the stream so that the work can be performed. So materialization is the act of allocating resources to the stream. It occurs when all stages in the stream are connected and the stream is run. Running the stream results in materialized values being produced. Each stage is then capable of producing a materialized value. Materialized values are separate from the elements being produced, transformed, or consumed from the stage. So your stream will go ahead and consume all of this data, running it through some function, but the materialized value that gets produced is separate from that consumption. In order to materialize a stream, you need an implicit materializer. We can get that using the implicit val materializer equals actor materializer. That in turn requires an implicit actor system in scope. We're going to go into more detail on materialization later, so if this doesn't totally make sense right now, that's okay. I just wanted to introduce it very quickly because in some of the exercises we will see materialized values and we need to have a basic understanding of what they are. So throughout the exercises we will be creating various graph stages, source, sinks, and flows. Typically the materialized value we will see is going to be not used, which basically indicates that it's not important at this stage. There are some exceptions to this, however. Sinks, for example, will often produce a different materialized value, and so we will see that in some of the exercises. And I believe we also make use of a source that produces a different materialized value. So just keep that in mind as we're going through. For this course, we're going to be doing a case study. The case study is called Akka Assembly. We will model a simple automobile factory. Our factory will receive parts, assemble cars, paint them, and finally run them through an inspection. Our job will be to build the stream components necessary to create the Akka Assembly factory. When working on the exercises, you'll need a few different commands. The man-e command displays the current exercise instructions. In addition, those instructions are actually available in the resources folder inside of a readme.md in the resources folder in the test folder. And we also have the show command, which displays the current exercise name. Next exercise will advance you to the next exercise and bring your instructions into scope as well as new tests, but it preserves any code that you've written. Previous exercise reverts tests and instructions to the previous state, again preserving your code. Pull solution will overwrite your code with the official solution, and save state will create a snapshot of your current code. Restore state will actually restore code from a saved snapshot, and then save states will list all of the saved states. So we're going to go through a group exercise where we're going to look at the existing code. Before we do that, this diagram here shows what we're trying to build. You can see the outer box is the factory, and then inside that factory we have a body shop, a paint shop, an engine shop, a wheel shop, an upgrade shop, and quality assurance. And then each of those has some number of stages involved with it. So the body shop just produces unfinished cars. That's basically a source. The paint shop, on the other hand, takes colors and then applies those colors to an unfinished car coming from the body shop. The engine shop receives shipments of engines and then installs them into an unfinished car as it comes into the stream. And so on and so on. So we have wheels getting installed, and we have upgrades getting installed, and we have inspections being performed. And then we have an auditor, and the auditor just provides functionality that allows you to audit portions of the pipeline, either by doing counts to see if the counts match what you expect, or by logging information about it. The end result of this, though, is we're going to take an unfinished car and we're going to produce a finished car. So we will build up each stage of the pipeline over the course of several exercises. We're going to start now by reviewing the provided code as a group.